It is a section 16.4 Corinth theorem. Every object in the world is bounded and has its own boundary. Physical quantities, for example, energy, can come into the object through the boundary, and energy can go out through other parts of the boundary. Total change of energy through the boundary must be the same as the total change of energy inside. So there must be a relationship between boundary integral and inside regional integral. Such a relationship has introduced a huge theory and many applications. The Corinth theorem is the beginning of such a theory. Let's see Corinth theorem. Corinth theorem gives the relationship between a line integral and double integral in two-dimensional domain. Okay. We'll begin with orientation of the curve. The positive orientation of a simple closed curve refers to a single counterclockwise transversal of C, as in this figure. So once you walk along the boundary, and if you can see the domain in the left-hand side, then the direction is positive orientation. For that one is a negative orientation. If you walk along the boundary, then you see the domain in the right side. Then it is negative orientation, and this is positive orientation. Okay. Here we have the Corinth theorem. C, the curve, is positively oriented and piecewise smooth and simple closed curve in the plane. And D is the region bounded by C, as in this figure. And C is positively oriented and D is inside. A vector field F has continuous partial derivatives on an open region, including D. Then the integral of the vector field can be evaluated through this regional integral. Now the integrand is q sub x minus p sub y. That's Corinth theorem, and it gives a relationship between the line integral and the regional integral. Okay. It can be proved by using such simple mathematics, but we'll not prove the theorem here. Okay. Now, once the curve is oriented for closed curve, then we'll try to use such a notation. Once the curve is closed and positively oriented, we may try to use such the notation. Over the integral, we make a circle, and that means it's positively oriented. This arrow can be outside. Once the curve is negatively oriented, then we can use this notation, or inside the arrow, down arrow can be attached in this way. Okay, so that if there is no, it is not mentioned, then default is positive orientation. So positive orientation, again, is like this one. Once you are walking along the boundary, then you'll see the domain in left hand side. Okay. Okay, let's try to solve this problem. Evaluate the integral. Now, C is triangular curve consisting of the line segment from 0, 0, 1, 0, now 0, 1, and coming back to the original position. Okay, let's try to visualize the domain. And this is now x and y coordinates. That is x direction, that is y. Start from 0, 0 and move to 1. And then now 0, 1 here. Okay, and coming back. So the curve is given this way. So it is a piecewise smooth curve and positively oriented. By using the Green theorem, we can evaluate it. Of course, for this one, piece by piece, you can parameterize, and now by using the technique we learned earlier, and we can evaluate this. However, let's try to use Green theorem. The given integral must be, now we call it D, then it's the same as region integral over D, and now we have to use, again, let's go back over the other theory, that is Qx derivative minus Py derivative. Okay, so that is Q, as x derivative is y, okay, minus, and this P y derivative, but that must be 0. Okay, and dA. Okay, so it is the same as the region integral over the y dA. Now this is a triangular region, and we can access this region, and for example, an outer integral x. You learned this one in earlier summer, and that is a kind of double integral accessing the domain once and only once without missing, without duplicating. So that is outer integral. X is moving from 0 to 1, then y is from 0 to here. Okay, so it is a kind of a vertical access. Now this one is the same as y equal 1 minus x, right? Okay, so that one, x is moving from 0 to 1, and y is moving from 0 to bottom y, top y is 1 minus x. And this is y and dy and dx. Right? Okay, from 0 to 1, and that is half y squared. Y is moving from 0 to 1 minus x and dx. So we can put half outside of the integral, and here that one is now 1 minus x squared and dx. If you try to evaluate this one, then that'll be, okay, 1/3. So the half times 1/3, so that is 1/6. That's the final answer. Okay. Evaluate the integral and over the closed curve, where f is defined in this way and c is the circle and oriented clockwise. So it is negatively oriented. So the given integral must be negative of the regional integral of now q sub x minus p sub y and dA. You have to put here negative because it's oriented clockwise. this is negative orientation. Okay, so inside of this circle is D. Okay, now let's continue. And over D, what is Q sub X? X derivative must be sine Y, and minus, and Y derivative, that is 1 plus sine Y. So the sine Y will be cancelled, and then that is same as integral over D, and integrand is 1 and dA. Okay, this is area of the disk, and center is 3 and minus 4, but radius is 2, so we can easily find the area. Radius to circle, area is pi r squared. R is 2, so that, oops, we forgot here minus, so that this is a minus, so that minus 4 pi, right? Okay. Yeah, minus, okay, over minus, okay, I'm sorry. Yeah, so eventually we have 4 pi. That's the final answer. Okay, here we have a minus 1, here minus, so it must be positive. Okay. Now, this Green theorem can be applied for the computation of area. We recall the area of region is integral over D with integrand 1. Now, if we can find the P and Q such that now Q sub X minus P sub Y is 1, then we can compute this one along with a line integral. So area of D is same as here integral, double integral over the 1 dA, which must be same as that on when PQ is satisfying this equation. So we have to choose PQ having this property. A simple example is when P is 0 and Q is X, then that will be satisfied. So this is one choice. Another choice is for P, we try to choose minus Y, and for Q, it is 0. So we have mainly two choices, and this is average. We can see it and how it is made easily. Now, so along with this choice, this integral is changed into that way, integral x dy. Along with this choice, now here p is minus y, and dx, and q is 0, so it disappears. So we have that one. This integral, that integral will produce same quantity, the area of the region. And once we try to make average, then that is exactly that one. It's the same as the choice here. P is half minus y, and Q is half x. So basically, these two are averaged to get this example. But this one is most popular one. Okay, we'll focus on this formula. The area of the region is the same as the closed curve integral x dy. Okay. Find the area enclosed by an ellipse given in this way. Okay. And once an ellipse is given, then we know that the area is AB pi. Okay, let's try to visualize here. assume A is larger than B. We have a major axis in X direction. So that is A and B. Then from high school, you learned this one. The area is A, B, pi. When A equal B equal all, then this one makes a circle, and then area of the circle is pi r squared. So that AB are r, then that must be pi r squared, right? So we know already the answer for this region. Now we'll try to compute this one by using the Green's theorem. Okay, so area of D, of course inside this is D, is same as integral and C, and if we consider C, then x dy, right? Now to get the integral, we may have to parameterize the ellipse. Okay, we have here good parameterization, and x is a cosine t, y is b sine t. Then here from this one, x over a is cosine t, and y over b is sine t, and this squared plus that squared must be 1. That's exactly this equation. Now, of course, t must be from 0 to 2 pi. So we have this parameterization. Okay, that can be evaluated through this parameterization. T is moving from 0 to 2 pi. X is a cosine t. And now there's y prime dt. Y prime is b cosine t and dt. So that is the same as AB, constant can go out from 0 to 2 pi, and cosine squared t, dt, right? Okay, now for this one, we may try to use the formula. It is half 1 plus cosine 2t. So that is AB, integral from 0 to 2 pi, and half and 1 plus cosine 2t and dt. T is moving from 0 to 2 pi, then 2t is from 0 to 4 pi. So this cosine, this portion will make 2 full cycles. And so because it is halfly positive and halfly negative, and in integration, the contribution must be 0. So we may ignore this portion. Now, the remaining integrand is half, and the interval length is 2 pi. So we have AB, and from the integral, we'll have pi. So we can get the right answer. So by using this formula, we can get the area quite easily. Now let's try to get the area of this shaded region, and we can easily see the area of this one. Now let's try to get the area. Okay, so part by part, you have to get the value. That is the first portion, second portion of the boundary, third one, and fourth one, and fifth one, and sixth, and finally we have seventh one. Okay, for the first one, integral, now c1 x dy, there's no change in y. So that must be 0. If you parameterize this, the portion, then y is constant, and dy is same as y prime dt. So that y prime is 0, we have a 0 value over there. So immediately we can see this portion is 0, and that portion again 0, that portion again, the contribution is 0. Now we go, so anyway, this is 0. And how about the second part? Okay, x is constant now. X is constant, which is 1, and dy. Now, dy is same as change in y is increased by 2, so that is 2. Now, for third part, and it can be parameterized in this way. Now, this line is y equal 3 minus x. Once x is t, then y must be 3 minus t. Of course, t is moving from 1 to 3. So that for 3, that is same as integral from 1 to 3, x dy, x is t, y is dy, so that there is y prime minus 1 and dt. Right? Okay, so from this one, now minus half t squared, and from 1 to 3, 9 minus 1 is 8, and minus half, so that we have minus 4. Okay, now it's 0, and how about fifth one? Again, same way, x is always 4, so that is now is 4, and y is moving from here to there. So change in y is 4. So the dy is 4. So that eventually that must be 16. And this is 0. Along this one, now x is 0. Of course, change in y is minus 4. It's go down from 4 to 0. But x is 0. So again 0. So let's try to write down the values here. For this one, it is 2. And this one, for this portion, is minus 4. For that portion, is 16. 0, again 0. So if we add them, then there is 18 minus 4. So that we have, okay, non-zeros are 2 minus 4 plus 16. So that it is 14. Okay, whole area is 16, 4 times 4, and this area is 2, so that exactly the area of this shaded region is 14. And along the theory, we found the same answer. Okay. Now let's go to another problem. Now we'll use this formula to get the area of this one. Okay, again, you have to do it piece by piece. For that one, x dy, no change in y, so must be 0. Okay, also for this portion must be 0. Now x is 0, so must be 0. Now you have to get this side. You can do this one in various ways. One is you have to parameterize this one, and beginning point is this one. So in this formula, now P is x is 4 and y is 0, and Q is this one, is 2, 2. Then that is R of t is here now 1 minus t and 4 and 0 plus t 2, 2, right? So that is same as now 4, 0 plus, okay, there is subtraction, then is minus 2 and 2t. So this is parameterization, and easily the integral, of course t is moving from 0 to 1, so that it becomes from 0 to 1, x is now 4 minus 2t, and y is in 2t, and y prime is 2 and dt. So by evaluating this, and you can get the solution. Now you may also parameterize this one using this one. Now that is, now y equal 4 minus x. So once you choose for xt, then y must be 4 minus t. In this case, t is moving, okay, 4 to 2, and the reason is the direction is like that. So x value is moving from here to there, and y value is moving along the line, so that you have to set this interval is go down. If you are using this parameterization, you will have to have that on. From this parameterization, now the integral, given integral is the same as now from 4 to 2, x is t, y prime is minus 1, and dt, right? So for that one, here half t squared, along with this negation, you can change the order, and 2 and 4, so that is 16 minus 4, right? That is 16 minus 4, which is 12, divided by 2, that is 6. Of course, the area of this region is 6. From this one, again, you will get the same answer. Now, we can get the line integral with this final technique. Okay, that one is, now you may try to get mid value of x and change in y and multiply. Okay, here mid value of x is 3, and change in y is from 0 to 2. 3 times 2 is the answer. So that is a numerical approximation now for this linear line segment, and we are using a second order approximation so that there's no error involved. So by using this technique, you can get it, and in your project, you will work on this technique. You can get exact value once the boundary is a combination of line segments, and there's no error involved. It's exact formula. Okay. Anyway, the area here is 6. Okay, we'll continue in the second part. Thank you.